So, let us get started. So, we are going to continue today on code generation first, and then we will see the dynamic programming approach. Yesterday we talked about the Sethi-Ullman approach for doing code generation of trees, which consists of two passes, namely the labeling pass and then the code generation pass. So, we will move further and then we will see one more approach for generating optimal code for trees. Okay. So, in this approach what you are going to do is that if you want to generate code for any operation, the cost of generating code for this operation is same as cost of generating code for T1, cost of generating code for T2 plus the cost of this instruction itself. Therefore, if you are asking for the minimum cost for generating code for this instruction, that should actually be based on the minimum cost for generating code for this instruction plus the minimum cost for generating code for this instruction and then the cost for this, right. In other words, this has this so called optimal substructure property of dynamic programming, right. In dynamic programming, what do you say? The problem is divided into sub problems and the sub problems satisfy the optimal substructure property, right. That optimal substructure property is essentially satisfied here because the minimum cost for generating code for this instruction is same as the minimum cost for generating code for this instruction plus the minimum cost for generating code for this subtree plus the cost of this. There cannot be any better way than doing this, right. If you take let us say a cost which is not minimum for a subtree, is there any likelihood that eventually you will end up with minimum cost? No, right. So, this satisfies this optimal substructure property and therefore, we could apply this dynamic programming approach and then we can get this. Okay. T1 and T2 can be executed in any arbitrary order, okay, and it may not have enough registers available. So, if you do not have enough registers available, okay, some results may be stored temporarily in a memory. That is really how it is. We will see how that is going to be done. Okay. So, the way that by which we proceed is as follows. For every node, we want to compute the cost of generating code for that node, okay, and then we want to, let us say if you have R registers, then what you want to do is that you want to find out what is the cost of generating code using 1 register, 2 registers, etc., all the way up to R registers. You also want to find out what is the cost of generating code for this and storing this result in memory, that also you want to find out. So, the cost of generating code and storing it in memory is same as the cost of generating code using R registers plus storing it in memory, right. That is really how we calculate that cost. Okay. So, essentially at every node we are going to have an array of costs, right. We will store in array element 0 the cost of doing it in memory and then 1 to R the cost of doing it, right, using 1, 2, 3 up to R register. So, it is basically an array of R plus 1 elements. That is really what we are going to do. Okay. So, as I mentioned earlier, the cost of computing it in memory is basically cost of computing it using at most R registers plus the store cost. Okay. Again, we are going to follow this contiguous evaluation, but there is a small twist here. First, what we will do is that we have to evaluate each subtree completely before you move on to the other subtree, but within each subtree, right, if some node has to be evaluated using memory, remember the memory cost is cost of computing it using R registers plus the store cost. That means that we must have all the registers available for that. Therefore, in each subtree what we will do is that we will first compute that particular subtree which requires it to be computed using memory, correct. That is when you will have all the R registers available. So, you first evaluate the subtrees of T that need to be evaluated into memory, right, using all the R registers, and then after the computation you put the value into a temporary location or into memory. Okay. Then you can do the rest of the computation for T1. Similarly, after you have finished this, you can now go to T2. And again within T2, whichever computation which requires to be done within the memory, you finish that, then do the rest of T2, then you go to the operation, right. So, this is the order in which you are going to do the code generation, right. Okay, this is specifically required again to ensure that you will be able to generate code with the minimum cost. Okay. This particular method generates code since it has to traverse each node exactly once, right. It has a cost which is proportional to the number of nodes in the tree. Okay. How many of you know about dynamic programming approach? Okay. What is the simplest example for dynamic programming approach? Simplest example? Dijkstra's algorithm. Wow. Huh? Fibonacci, right. Fibonacci is the simplest recursive evaluation of Fibonacci is the simplest example. And what do you do in that thing? Essential idea of dynamic programming is that you memorize the correct, right. You memorize the Fibonacci values of the previous two numbers. Okay. Therefore, it needs to be computed exactly once for each number. That is why it has a computation cost which is okay. Now, let us see how we are going to do this dynamic. Again, the dynamic programming approach, we are going to exactly follow the same thing, right. If I want to calculate the cost of this subtree, that is going to in turn going to go into the cost of two subtrees there, correct. And then that in turn is going to require cost of computing subtrees there and so on and so forth. And at each point in time, I actually store the cost of, right, the minimum cost for generating code for that subtree using 1, 2, 3 up to R registers as well as using memory. So, and then I keep using this upward, that is how we memorize these values and then keep using it upward, so that it traverses the tree exactly once to get the cost. Okay. Now, let us see how that works. So, essentially you are going to compute the cost bottom up manner, right, starting from the leaf nodes, right. And let us assume that this is an array of n to r plus 1, it should have been r plus 1, okay, because there is also 0 for each node where you have r registers, okay. And Cn of I is the minimum cost of computing the complete subtree which is rooted at node n, okay, using I registers, okay. And when you do this thing, you also have to find out, once you have found out which has the minimum cost, you also remember what kind of gives you that minimum cost, what combination gave you that minimum cost, so that when you generate code you can use that combination to generate that code. When I give you an example, this will become clear, okay. Now, using this cost array, you determine the subtree that must be computed into memory. If any subtree requires to be computed into memory, then that subtree has to be, then the code for that subtree has to be generated first, okay. And then of course, the rest of the subtree, that is the order in which you are going to do, okay. Let us see, again we will take the same example and then start computing the cost for each of the nodes. Again, computing the cost is going bottom up. Remember, in the Sethi-Ullman algorithm, when you are doing labeling, labeling was bottom up, okay. That is exactly the same thing that you are going to do, right. And now, let us look at the cost for each one of these leaf nodes to start with, right, okay. If you know that each leaf node is going to be either a variable which is in memory or a constant, correct. If it is a variable which is in memory, then computing it with using memory is actually no cost, right, because it is already in the memory. If it is a constant, it is a constant, we can actually use it directly in our this one as long as it is a small constant, okay. Now, let us look at this. So, this node A is basically a variable, right. To compute this using memory, it requires no cost, but to compute it using one register, you need a move instruction, correct. Therefore, that requires a cost of 1. Computing it using two registers is same as one register, because you do not need the second register, so you can just not use it at all, right. So, the cost of computing any node, right, any leaf node which is actually in memory is basically 0 for memory and 1 for the first register, and any other register also it will be 1. So, here we are going to do this example again using two registers, that is why you have 3 elements for each node, okay. So, that explains this 0, 1, 1 cost for all the leaf nodes, okay. Now let us see how do we compute the cost for T1. Okay. Now the cost for computing or generating code for T1 using one register, we will do that first. Okay. Now if you want to compute the code using one register, one possibility is that you can give one register for T1, okay, and no register for B, right. Remember that the right operand can be memory, left operand has to be a register. That means that using one register the cost of computing A is 1. Using 0 registers or using memory which is already there in the memory, the cost of computing this is 0, right. Therefore, the cost of computing T1 is basically 1 plus 0 plus 1. 1 for this, right, loading A into memory, loading A into register, another for B which is already, nothing for B because B is already in memory, and one for doing the add operation for T1. Okay. So, that is the cost of evaluating or generating code for T1 using one register for A and using 0 registers for B. Okay. How about using one register for B and 0 register for A? Not possible, because the left operand has to be in register, right. Are there any other possibilities?
Why can't you use same register for A and T1?
Huh?
Why can't you use same register for A and T1?
A and B1.
T1.
A and T1 you can use the same register. Remember, this is the cost of generating code, not the number of registers, correct. So, cost of generating code with one register, even this is with one register, not with 2 registers, right. I am basically including the number of instructions. Cost is here is the number of instructions, not the number of registers, okay, correct. And we have to consider all possible instructions and operand modes or operands for this. That is why we consider register operand for this, memory operand for this. Memory operand for this, register operand for B is not possible, okay, right. So, this is the cost of computing this element. Remember, this subtree and this subtree are the same, okay. So, whenever you fill the cost for T1, you can also fill the cost for T2 appropriately, okay. Now, let us find out what is the cost of doing T1 using 2 registers. Now, there are several possibilities. You can compute A in one register and B in one register, and when you do that, the cost of computing A in one register is 1, cost of computing B in one register is 1, and the cost of computing T1 is 1 more. So, there is one move instruction for this, one move instruction for this, and possibly an add instruction for this, right. That cost is 3. Now, if I am given 3 registers, I can give both registers to A and no register to B. Does not sound like a good idea, but let us see what is the cost of this, right. In this case, since B is the right operand, okay, it can be given 0 registers and it can be taken from memory, and that actually gives me a lower cost, right. Therefore, if I give 2 registers to A, 2 registers to B and then no registers, or 2 registers to A and no register for B, then essentially I am computing this using 2 registers, which is same as computing it using 1 register, plus computing this in memory, which is 0, and then adding up these two things along with the cost of T1. So, that cost will be 2. Now, let us look at this interesting possibility which we have not seen before, correct. Remember, when we did code generation for trees, what did we say? If the left subtree has particularly the labeling algorithm of Sethi-Ullman, what does it say? That there are 2 subtrees, okay. What is the minimum number of registers required for the node? Let us say if the left subtree requires R1 registers, minimum registers, the right subtree requires R2 minimum registers, what would be the cost of generating, what would be the minimum number of registers required for the root? Correct, correct. Why did we say that? If they are not equal, what did we say?
Because we can compute the result requiring more registers first and then keep that register and use the other.
Exactly, right. So, now remember that I should not simply say that if I give 2 registers to A, after computing A, I cannot need to keep the result only in one register. All other registers can be released for B. Okay. So, that is this possibility. I give 2 registers to A, I first compute A, correct, and then after finished computing A, I can release all but one register, and that register can be used for B, and I can evaluate the cost. So, I need to consider this possibility also, saying computing A using 2 registers and computing B using 1 register. Do not treat this as 3 registers, right? It is not like 3 registers, right. If I have 2 here and 1 here, then this will be only 2. If I have 1 here and 1 here, this will be 2. That is true, right. So, you have to remember that possibility, and you also have to include that. Therefore, the cost of computing T1 is the minimum cost of 3, 3 or 2, which is 2, right. So, when you do this thing, what you really need to do is, I will show you, right. So, here what we have calculated is that for T1, we said that the minimum cost is this one, A in a register and B in memory, right. So, what we need to do is that here we need to show A in register, B in memory. I am sorry, let us do this not here. So, this is for 2 registers, correct. So, here we will say A in register, B in memory. Okay. This information is something that we need to save, so that when you come to T2, if you choose 2 registers, okay, it means that you have to use this particular option, correct. You need to remember that, otherwise you would not know how you have arrived at that. Similarly, of course, for this also you need to remember, right. Here what you say, here A in register, B in memory, correct. So, you need to remember these things, right. Every time you store the minimum cost, you say which pattern has caused this minimum cost. In this case, the pattern which has caused this minimum cost is this one, right. Therefore, you save that information over here, right. Okay. Make sense? All right. Now, let us move forward and then see how do we compute this. So, moment I do, okay. Now, the last thing that we need to find out is what is the cost of evaluating T1 in memory, which is the third thing that we need to see, right. Evaluating T1 in memory is the cost of evaluating T1 using OR registers plus storing it in memory, right. So, that will be 2 plus 1, okay. Make sense? So, now you have finished this 3 2 2, you also know that this will also be 3 2 2. Now, let us take one more example and then see how that works. Let us look at T3 and then look at evaluating T3 with 1, 2 or 3 registers. See, remember, whenever you are evaluating the cost of generating code for a particular node, you need to consider all possible combinations, okay, and you need to consider for all possible registers from 1 to R. I do not think that using OR registers is going to be cheaper, right, than using, is likely to be cheaper than using R minus 1 or R minus 2 registers. There is no reason for that. For example, here you can see, right, using fewer registers, right, using only memory is actually expensive in some cases. It could be, I mean, using, sorry, the other way around, should have said the following thing, using fewer registers may not necessarily be more expensive than using more registers, okay. That is really what it is, okay. Now, let us look at this particular example shows you that, right. Let us first find out cost of evaluating T3 with 1 register. If I have 1 register, right, obviously the left child has to be in the register, the right one has to be memory, okay. But then what does it mean? I could have actually done the following thing, I could have computed the right child using memory and put it in, sorry, right child using 1 register and put it into memory. That is also possible, correct. Given that I have 1 register, I could have first computed T2 using that 1 register, put the value into memory that means that eventually everything is in memory, and then use that one register for this. So, when you say cost of evaluating this, okay, using one register, you could have given that one register to E, and then you could have calculated T2 in memory, right. That means that this cost would be one register, which is 1, calculating this in memory, which is 3, plus cost of this instruction, which is 1, which is 5, and that is this cost, okay, right. I mean that actually we will find out, that has to be the minimum. Are there other possibilities? Again, there are no other possibilities. I can't calculate both of them in memory. I cannot calculate this in register and this in memory, that is not possible. So, among the possibilities, this is the only possibility among this, and that possibility gives me a cost of 5. Okay, therefore, this one is 5, and I have to remember that this has to be computed in one register and this has to be computed in memory, that is this cost plus this cost. Okay. Now, let us find out cost of evaluating T3 using 2 registers, right. Again 2 registers, there are several possibilities. Let us find out which one is going to cost the minimum. Okay. I have only one example done here, maybe we can quickly work out the other. So, if I have 2 registers, I could have given one register for this and one register for that, correct. Now, one register for this and one register for that would add up to 1 plus 2, 3 plus 1 more, which is 4, correct. So, that is one possible value. I could have given 2 registers for this and 0 registers for that, that will add up to 1 plus 3 plus 1, which is 5, which is higher than 4. So, there is no point looking at it. Any other possibility? I could have given 2 registers for this and 1 register for that, that is also a possibility. Remember, when I put 2 1, right, this still has 2, right. If I put 2 here and 1 here, then it is again 1 plus 2 plus 1, 4, which is same as the minimum cost. So, here when I put this 4, right, I could store that one register for this, one register for that. Typically, that is a better option than saying 2 registers for this and 1 register, right. Both of them giving me the same minimum cost. So, I might as well put the first one. Okay. Now, after having done this thing, we have to calculate the cost of evaluating this in memory, which is same as the cost of the minimum cost across 1, 2, 3, 4 or registers plus 1, correct. Yeah.
We are calculating 3 values for every node because
3, sorry, we are calculating
we are calculating 3 values for every node.
Yes.
That is because we have 2 registers.
That is because you have 2 registers.
If we had more, we will calculate.
Absolutely, absolutely, right. So, this, as you will see, that it is dependent on the number of nodes and the number of registers, correct, right. So, it is going to be order n into r. Okay, now, let us look at T4, correct. So, calculating T4 with one register is calculating this with one register and this in memory, right. So, that would be 5 plus 2, 7 plus 1, 8, right. If you have one register, that is the only possibility because you can't give the register to the right side. Now, let us look at if you have 2 registers, then you could have given 2 registers to this and 1 register to that. Okay. That is 2 plus 5, 7 plus 1, 8, or you could have given 1 register to this and 1 register to this. Okay. That is also 8, right. 1 register to this, 1 register to this, that is also 8. Okay. Let us look at how do we get 7. You give 2 registers to this and 1 register to this, right. And when you give 2 registers to this, right, you can first evaluate this particular subtree and then release all but 1 register and then use that register to evaluate this. Okay. That can be done, isn't it? And when you do that, it is 4 plus 2, 6 plus 1, 7, that is the minimum cost. Again, here you will save all the patterns. For 8, what is the pattern, right? 1 here, 1 here. For 7, what is the pattern? 2 here and 1 here, not 2 here and 1 here, right. So, we have to say, for example, for this one, okay, 2 to 2 registers to T3, 1 register to T1. You have to store things like that, right. And when you do that thing, if you are going to generate code for this instruction, correct, what is the assumption? You are giving 2 registers here, 1 register there. And the moment you do that in code generation, what do you have to do? You have to generate code for this subtree first before you generate code for that subtree. And just give me 1 minute, I will take your question. And within this subtree, if any of the nodes kind of keep a pattern saying that it has to be evaluated in memory, then that has to be evaluated first, except for leaf nodes, because leaf nodes doing it in memory is actually nothing, right. For example, here, right, you are going to do it in memory, but that is really nothing, you do not generate any code for that. But for all other internal nodes, if something needs to be done in memory, then for that code needs to be generated. Yes sir, question. Your question. Two registers to T1, right, and 1 register to 0 registers. Okay, 2 registers will give you this, and 0 registers will give you what? It's actually not, when you give 2 registers to here, you can as well give 1 register, but that 1 register also could be including memory cost. Okay, you can consider either 1 register cost or you should consider memory cost, whichever is lower, right. In fact, what you will do is that you will actually look at this entire array, and then if you are looking at some k registers, you will look at all values k minus 1, k minus 2, etc. up to memory. Okay, whatever is the minimum cost we can take, because doing it in this many, in fact you would have done that already, because this minimum cost itself would have worked out that way. Okay, doing it using that many registers, 1 k minus 1 registers, right, is actually what it is. So, it is fine. Okay, it would have effectively result in this scheme. So, in this case, if you give 2 registers to T1 and only 1 register to T3, you are either going to choose this pattern or this pattern, okay. And unfortunately, these 2 patterns are going to result in a higher cost, whereas what you want is this, and if you want that, you should have given 2 registers to T3 and 1 register to T1, and that means that you have to evaluate this subtree first before evaluating that subtree, right. Any questions? Okay, so let us now, so this process is basically computing the cost, right, for all the nodes. Now we still have to generate code. Remember, computing the cost is bottom up, and generating the code is going to be top down. So you look at this, for every node choose that particular value which has the minimum cost, right, and then for that particular minimum cost you also know how to generate code. For example, for this 7, we saw that you have to allocate 2 registers to T3 and 1 register to T1, and the moment you say 2 registers to T3, you know that you have to evaluate this subtree first, correct. Therefore, the moment you say that you have to, I mean, of course, the code generated is going to be the other way around, okay, you will not generate code like this, but here the code that has to be generated is something like this is going to be, well, let us actually do it the other way around, right. Then you come down, right, and then you say that next I have to generate code for T3 before generating code for T1, right. Now, how do we generate code for T3? Again you look at it, 2 registers, okay, that is the minimum cost, and you have to use, right, for that whatever is the pattern, then you will follow. That pattern might be 1 register here and 1 register there, right. and this one register mean move this to blah blah and then do this and then do this, then you come to this side. Then here you will say that I have to use one register which will be move a comma into some register and do this. Again you will try to see whether you can evaluate this in the same way, that the left subtree value is evaluated in the same register as the destination register, right. The ordering that in way in which I have given is basically to remember the pattern, not to generate the code. Obviously you have to generate the code from the leaf node to the, it's not bottom up, it is top down, but it is a recursive procedure. It will go to the leaf node, generate code and then go to the parent node. Remember the code generation mechanism that we saw in the labeling, and you were trying to do the swap registers and other things. It's something very similar, okay. That's really what happens here, okay. So we are not going to go through the code generation process in any more details other than looking at this level of detail, right. All right, any questions? Yeah.
What advantage or dynamic programming approach gives over secure?
Two different approaches, that's all.
Complexity wise both
Complexity wise both
are the same.
are going to be more or less the same, yes.
Space for the dynamic programming approach will be more.
Space meaning?
Additional register for the array of R.
Yes, yes, yes. So whereas that is a labeling approach, yes. Okay. I am not really sure whether there are any other advantages of dynamic programming, I do not recall, but yeah, they are somewhat similar approaches. Yeah.
How do we remember which combination of registers is to be?
So that is also going to be stored in an array along with that. So you have the C array which is the cost array, and similarly a P array which is, let us say, the pattern array, which will store how to distribute the registers for that particular cost, right. We did not explicitly talk about that, but that cost is included, which adds to his point, more storage cost, right. Any other questions? Right. We will see one more mechanism for generating code, right, and that is the tree pattern matching approach. This also allows you to select appropriate instructions. Remember when we talked about this code generation scheme, the dynamic code generation scheme, or the dynamic programming approach based code generation scheme, for each node not only you consider these different possibilities of which register to be given to what, you can also think in terms of what other instructions can possibly implement this. That also needs to be looked at, okay. Of course here we do not have an example which kind of meets that, but for example let us say if this is a plus 1, right. When I give you a example for tree pattern matching, it will become more obvious, but let us say for the time being that this is computing a plus 1 instead of a plus b, right. Then in that case it would have been better to do an increment operation, right. And if the architecture allows you to do an increment operation even in memory, then that is even better, because it will actually have a cost of 1 for this entire subtree, correct. Otherwise you have to move it into a register, increment 1, but if it allows you to increment it in memory, then you could have actually done this using that. So again it depends, so you need to consider all possible combinations, but it can still be done. Now let us see how tree pattern matching essentially does many of these things and allows you to do appropriate instruction selection as well, okay. So that is the next thing that we are going to talk about, okay. So there are many different possible ways by which we can select the instruction, and choosing the appropriate one is a complex problem, right. And you do not want to kind of manually also write many of these code. Again different possible addressing modes are there, that also complicates the matter, and there are different possible instruction combinations that can also generate code for the same set of instructions. And lastly we want to see whether this process of writing the code generator itself can be automated, right. For example, let us say you wrote a code generator for architecture A, but tomorrow you want to write a code generator for architecture B. Do you have to go ahead and rewrite that entire code generator for architecture B, or can architecture A and architecture B specified in some way and there is a code generator which generates the code generator for A and the code generator for B. Can we do that? It is possible to do that also, and this kind of an approach where you try to do instruction selection using tree pattern matching enables you to do that. In fact, we are going to briefly talk about two code generators which are very popular. Okay. Before we go into those details, let us first look at how this tree pattern matching based code generation works. For this, we are going to use this intermediate representation which is called the tree intermediate code. Tree intermediate code is nothing but a DAG like structure or a tree like structure. It is a tree like structure, not a DAG, it is a tree like structure. Okay. And let us see an example to understand this. So, this is the statement, intermediate statement that I want to, for which I want to generate the code. A of I is equal to B plus 1, right. And let us try to understand this tree representation before we go to anything else. And in this particular example, let us also make sure that we understand what these variables are. Let us say A and I are local variables. What do we mean by local variables? Where are they stored? They are stored in the stack frame, and when they are stored in the stack frame, they are going to be referenced with reference to the stack frame address, correct. That is really what we need to understand. And let us say that variable B is global, that means it will be in the data segment. Okay. Okay. Now, let us remember these things and then see how this tree pattern thing works, right. B plus 1, right, 1 is a constant, B is in the global memory, right. B is a global variable, therefore it is in the data segment, correct. And if you want to load B, either you need to have the address of B and then move it using some instruction into a register, or you could take the address and then directly use that memory location, right. Again, you have to think in terms of what addressing modes can be done, right. If it is in the data segment, then to access B, first thing is that you need the address. Address is going to be 32 bits or more, correct, right. Okay. As opposed to, let us look at this I, right. Here also I need the address of I, but this I is a local variable, it is in the stack frame. So, when it is in the stack frame, this location is going to be relative to that stack pointer location. So, how do I specify the address now? Stack pointer plus minus some offset. So, what is that addressing mode? It is called the displacement addressing mode, correct. So, here I do not need the absolute address of I, whereas here I need the absolute address of B if I want to load it, correct. Whether I use the memory or I use it, or I move the contents to a register, for me to access B, I need the address of B, and here the address of B can only be specified as an absolute quantity, 32 bit number or higher. Whereas, to specify the address of I, it is much simpler. It is going to be a small offset from the stack pointer. So, I can use it using a displacement addressing mode, and in the displacement addressing mode, my offset is going to be a small constant 4, 8, maybe 32, maybe 48, whatever number it is, but it is still less than a 12 bit or a 16 bit number, and therefore, I can actually use that index addressing mode, correct. Having said that, right. So, at this point in time, of course, we are not taking the decision, we are saying that what is the offset of I, right, and that offset has to be added to the stack pointer in order for me to get the address, and then I index that address, that means that I dereference that memory location to get the value, and that value would be I, correct. Similarly, if I want to find out A of I, correct, and remember this is the left hand side, that means that we are interested in the address and we are going to store the value in that location. How do I find A of I? Let us assume A is an array of characters to make things simpler, right. How do I find A of I? I need to have address of A plus add the offset corresponding to I. Since it is a character, each location requires only 1. If it is a short or an integer, what should we have done? Sorry? Plus 4. What should be multiplied by 4? I should be multiplied by 4, correct. So, this value that I have dereferenced should have been multiplied by 2 or 4 depending on whether it is a short or an word, and then that value should have been added to the address of A. How do I get the address of A? A is also a local variable, it is also in the stack, therefore, it is going to be offset from the stack pointer by a small offset. That offset needs to be added to the stack pointer, and that gives me the value of address of A, and to that address of A I take this offset value and then I add it. I get the address of A of I, correct, right. If I index it or dereference it and get the value, then of course I would have got A of I, but in this case what I need to do is that I have to dereference and then store. So, it is not a read, it is a write, but you are computing the left hand side of this expression. Okay. So, to that particular location, what am I going to write? I am going to write B plus 1. Okay. So, do we understand how this tree pattern thing working? No, sorry, not the tree pattern, the tree intermediate code working, right? Any questions?
We are using stack pointer to calculate the address of A and also for
Address of I.
So why do we have the stack pointer as two different leaf nodes in the
Oh, why do we have this as two different leaf nodes? Why not we put this as one leaf node? Okay. The first thing that would have happened is that this tree would have become a DAG. Okay. Second thing is, since it is a leaf node, the cost is not something that we are going to worry about. So, it is okay to duplicate that. You could have put that, essentially you could have put this pointer over here, nothing would have happened except that suddenly the tree has become a DAG and you are stuck with it. Okay. We will see what happens when you have a DAG, because in practice, right, when you generate either the tree intermediate code or when you generate the dependence graph, they are going to be a graph rather than a tree. Okay. And in those cases this optimal algorithm is not going to work because they are no longer tree, right. We will see what to do with that, but for the time being we will just duplicate these things because it is not really different, it is only a leaf node. Okay. Any questions? We move forward. Okay. Now, given this, let us see how the tree pattern matching is going to use this tree intermediate code for generating code for this. Okay. So, the tree pattern matching starts off with a set of patterns which are defined, and for each pattern it gives you what is the code to be generated and what is the cost for that particular pattern, right. For example, if I have a pattern which says a constant has to be moved to a register, right, that pattern would cause the code generated to be like move constant to register I. Similarly, if I have a pattern like a memory location has to be moved to a register, then that is load A to RI. If I have a pattern which says that memory location needs to be stored with the value of a register I, right, then that would look like, that would generate a code store of RI in memory location A, right. Let us look at more patterns. Here actually I have not being careful, okay, that has to be a store, right. Okay. We will come back to this little later. I will try to find out what is the mistake in this. I was thinking it is a store, but then you do not have, if it is a store then this should not have been there, okay, this should not have been there. Okay. So, maybe without this you can actually think of this. If you have this pattern, right, register J, use the value of register J to index, I will use this pointer here. So, for example, right. You have the value of register j which is used to index, that means that you are dereferencing, and in that location you want to write register I. So, that is basically store R I into indirect location R j. Now, this is a simple thing where you are basically adding two registers, okay, and when you do this the result goes to register. Okay. So, this essentially says the value goes to register, that is memory, that is really what it says. See, okay. Yeah. Okay. So, yeah. Now, there are more things here. So, for example, if you have a register and you want to add a constant 1 to it, then you can say that add #1 to Ri, or you could have actually replaced it by increment instruction if such a thing exists, right. And here if you want to do constant plus register, then it is also increment and so on. Okay. So, like this for all the instructions and possible combinations you generate the patterns, okay, and all of these patterns can be expressed as grammars. Okay, that is very important because later on you will use these grammars and then write these code generators. Okay. Now, let us look at how these patterns are going to be used in order for us to evaluate this expression. Okay. Now, let us first start off with this address A, right. Now, that address A, okay, remember that this is a offset value which has to be added to the stack pointer, okay, right. So, what I can do is that I can move this small offset into a register. Remember the left hand side has always has to be a register, right. So, I can move this into a register. So, the pattern that I find here is that there is a pattern which is saying constant A to register. If I apply that pattern, right, that matches with this, okay, and therefore, I can say that the corresponding instruction for this is, right, load #A. Remember #A is the offset that we are talking about, has to be moved into a register or not, right. This is already in register. So, I do not need to, this is stack pointer, register stack pointer. So, this is already a register. Now, if I look at it, this pattern is something like register 0 plus register stack pointer, right. So, register per register and that going to a register, the corresponding pattern is add or not comma stack pointer, right. Now, the next step, you are now replacing this by a register because that is how the code has been generated, that value is available in R naught. Now, what about the code for this entire subtree now, right. There are two possibilities here. One possibility is to look at this subtree first, and that subtree can be matched with this pattern which says that register I, okay, register I is equal to index of constant plus register j, right. So, you can just see what that is. Okay, let us look at this. This address I is going to be a small constant that has to be added to a register stack pointer. So, that is essentially constant plus register j, right, and then that has to be indexed and that value going to a register. Okay. So, if I look at this particular subtree, then that subtree can be matched by this pattern matcher to this pattern, and you can generate code for this, okay, and there is a cost that is involved for that. Whereas, you can actually look at this entire subtree, okay, and you can match it with this pattern, right. Again, look at this part is very similar to this part, okay, but then this register I plus indexing of this, right, and going to a register is possible, right. Why? Because my left operand is a register which is this value, and my right operand is a memory location. That memory location is actually expressed in the displacement addressing mode, correct. So, small I, small offset, SP, I mean small offset essentially tells you how far away is I from the stack pointer, and then when I add this to the stack pointer, correct, I get the address of I dereference it, I get the value of I. Okay. So, if I look at this entire tree, it can be matched using this pattern. In other words, what I have is that I have this pattern in my pattern matching table, and the pattern matcher essentially looks at the tree and then tries to find out how to find a pattern that fits with the various patterns that are described in that, and then it tries to choose the maximum pattern or the pattern which gives you minimum cost. Typically maximum pattern gives you the minimum cost. So, if I can do that, then the code for this entire thing is actually now this P. Okay. So, that essentially means that this whole subtree can now be replaced by a register which is in R naught, right. So, let us do that. Now, what we have is that we have this subtree for which we need to generate code. Now, again look at this, this is memory and this is a global location. Therefore, first thing is that we need to move the address of B into a register, right, and then we have to increment that register, right. This has to be value B because you have to increment B, you are not supposed to increment the address of B. Okay. So, again look at this, what do we have? We have mem of B, right, and in order for me to find out mem of B, what I need to do is that I have to load the value of B into a register. I do that using this instruction load B comma R1, right, and then of course I have register plus 1, I can generate the increment instruction. Now, that will replace this by a register, this already is a register with an index, right. Now, what we can do is that this is equivalent to doing a store instruction, that is store this value in the location pointed by this register. So, that completes the code generation for this, right. So, essentially what you have here in the tree pattern matching based code generator is that the the code generator has a set of patterns, right, and for each one of those patterns you also have this information about what is the code to be generated and how much cost it requires. Then the tree pattern matcher essentially walks through the tree and then tries to reduce each part of the tree or subtree, right, to a pattern, and then for that pattern what is the cost. Like that it tries to cover or complete this entire tree. That is really how the tree pattern matching based algorithms work. We are not going to go into the details of how to write that pattern matcher and how to specify the patterns and things like that, just to give you an idea of what it is. Several of the code generators are based on pattern matching code generators. Okay, that is the point that we need to remember. Any more questions? Okay, now let us move forward. Okay, as I mentioned earlier, this is something that, yeah, okay, oh sorry, this is slightly different topic. So, now let us address this question of what happens if my basic block results in a DAG rather than a tree. If it is a tree, we have good solutions available, but if it is a DAG, what do we do, right? Okay, so for this optimal code generation is NP hard, so we may not be able to generate optimal code. So, we have to use some heuristic to generate efficient code, right. So, one possible way is to look at your DAG and then split some of these nodes so that your DAG becomes a tree, right. Let me give you an example here, right. Supposing let us say that we have something like this, right. It is a tree except that this particular node is shared, right. Now, one way to make this a DAG is to replicate this node. So, if I replicate that node, then it becomes something like this, with this removed, correct? Then it becomes a tree, right? Then I can generate code for this tree. But when I replicate, what happens is that I will generate code for this part and I will again generate code for this part, which is redundant, and it will increase the cost of my code generator. Okay. Another way of doing this is not so much replicate, but generate code for one part, do not do this, right, generate code for this part, store it into a memory location and use that memory location in the other one. So, that is the other way of doing it. So, instead of repeating the computation twice, you kind of do the computation once and then store it in memory, and in the other side you essentially use it. Okay. That is the second part. Compute the shared tree once and then save it in memory and reuse. Okay. This in general works for a class of machines, but again you have to remember that this may not necessarily result in the optimal code again, right. Okay. Now, the next point is about code generator generators. As I mentioned earlier, writing code generator is fine, but if you have to write code generator for machine A, then code generator for machine B, then code generator for machine C, you do not want to repeat this exercise again and again. So, can we actually automate this code generators itself, right? So, for that typically you use this tree pattern matching based approach and dynamic programming approach. So, you kind of combine these two things. Using tree pattern matching, you kind of find out what is the minimum cost for each subtree, and then using that you kind of apply it in the next higher level. Okay. So, essentially it accepts tree patterns, associated cost, and the semantic action, which is essentially the code generation, and then using some kind of a grammar you express these patterns, and then you kind of write you write the code for a tree matcher, which kind of goes through the graph, which kind of goes through the tree and then identifies what can be matched, but you also have to cover this entire tree and you have to find the one which covers it using the minimum cost. Okay. So, the first pass is the bottom up pass, which finds a set of patterns that cover the tree with the minimum cost, and the second pass execute a semantic action, which is basically generating the code, and that is typically the top down part. Okay. So, there are a few code generator generators, Twig, Iberg and Berg and Iberg. Okay. These are kind of popular code generator generators. Unfortunately, we are not going to go into the details of this in this lecture. Okay. So, you may want to look up what these things are. So, essentially the entire process of writing a code generator itself can be automated, and if you have a code generator that will actually do similar to what you have seen in lexical analysis and right lex and yak. So, you no longer write these lexical analyzers, right, there are programs which can generate these things. Okay. Now, let us look at the last part. After having done these things, you end up with the so called machine code. Now, is it guaranteed that this machine code is supposed to be very good, or will it also have some opportunities for optimization? Okay. Let us look at it, and then that kind of optimization opportunities can be addressed with what is called the peephole optimizer. Peephole essentially means a small window. So, what you do is that in this generated machine code, you look at small windows of instructions, and within that small windows of instructions, if you identify certain patterns for doing optimization, you apply those optimizations, right. So, these optimizations are effectively local optimizations, because you are looking at a small window of instructions, okay. And this is typically carried out on the machine code, but sometimes one could also apply this on the intermediate code. Okay. As I mentioned earlier, it is going to look at a small window, but it is a sliding window of code, which is what is called the peephole, and then it tries to apply these optimizations. Okay. Each improvement can itself in turn lead to additional improvement. So, you have to kind of repeatedly apply these things, like in many of the other optimizations. Okay. Now, these are some of the optimizations that are possible using peephole optimization. Okay. For example, eliminating redundant instructions, eliminating unreachable code, eliminating jump over jumps, algebraic simplifications, strength reduction, and certain machine idioms. Okay. We will see examples of some of these things in order for us to understand. So, for example, let us say that the code generated has a load instruction and then subsequently a store instruction, and between this load and store instruction let us assume that x was not that R1 was not modified, right. That means that I am loading a value from memory into R1, I am using it multiple times, and then again I am storing it into memory. Obviously, this is a redundant instruction, it can be eliminated, right. Now, let us look at this piece of code, right. I have condition equal to 1, if condition equal to 1 go to L1, do this, right. Now, will this code be ever executed in this situation? No, right, because condition is 1 and then you are going to go to L1. So, if you do constant propagation, then this becomes 1 equal to 1, which is always true. That means that you are going to go here. So, this is an unreachable code, it can be eliminated, and if this code happens to be just following this, then all of this can be eliminated, right. This condition can be eliminated, this add can be eliminated, but if there are whatever instructions that are here, you can actually eliminate all of them as well, because they are all dead code, right. So, let me just since it is always going to jump from here to here, any instruction that you see here, right, like the add or any other additional instructions that you hear, they are all redundant and means they are all dead code. So, they are never going to be reached and you can eliminate them, and the moment you eliminate this, your L1 is directly below this one, correct. Therefore, this condition is also redundant and can be eliminated, right. So, that is why you apply this Peephole optimization repeatedly, right. Jump over jumps, yeah, sorry, question. In the intermediate code, possibly it would have been done in the intermediate code, but there are certain things that you do during code generation that would have caused some of these things to happen also. It is to answer your question, you try to do some of these optimizations in the intermediate code, and then you take the optimized intermediate code and generate the machine code. But in the process of generating the machine code, right, again these opportunities would possibly arise because of the way in which you are generating machine code. See, I can give you an example for this, just saying that this let us say that we are trying to compute something, right. I will give you an example of this. For example, let us say that x is let us say that we have a variable which we were spilling, loading and then again spilling, and then loading and then again spilling. If you are doing that, right, it may be the case that I have been loading and again I am trying to spill. In between there were no modifications that were done. If there are no modifications that were done, then there is no reason to store it. So, this can be eliminated. So, there are these opportunities that do arise, and typically a simple Peephole optimizer pass which repeatedly goes through this code kind of cleans up this. So, here is another example where you have what is called a jump over jump. Okay. So, here you have a less than b, go to L1, and then in L1 you say go to L2, right. If you look at these two things together, you could have replaced this and then said go to L2. Strength reduction essentially says that instead of using some more expensive operations, you could have used, right, other operations. Again, you could ask these questions, wouldn't instruction selection have taken care of this? Yes, it could have taken care of this, but then if that didn't consider it for whatever reason it is, then these opportunities do arise. See, for example, when you are generating code, right, maybe this 8 was not a constant, right, and then maybe you did some constant propagation like what you did over here, and then that resulted in this value being 8. Now, you have an additional opportunity of doing this. So, whenever you have this multiplication, you can replace multiplication of a number which is 2 power 8, 2 power k, then you can replace it by a shift operation. Similarly, power operation can be, I mean power will not happen in the machine code level, but yeah, similar things like what you have seen in strength reduction, right. Again, machine idioms where you can actually replace certain things. For example, here we are loading x to R naught, incrementing R naught by 1 and storing the value, correct. So, we could have replaced this by a increment instruction if the machine supports an increment instruction. So, these are opportunities that you get in code generation and you can actually exploit them, right, and you can eliminate some redundant code or optimize your code. So, this optimization is the last phase after, I mean last in the sense of after code generation you do one more pass of peephole optimization and eliminate some of these redundant codes, right. That is something that you do. Okay. That kind of completes our discussion on code generators. So, do you have any more questions on this? Yeah.
There are industrial compilers like Clang and GCC which are retargetable. They have multiple machines that they can target, and all of these machines will have very independent code generations.
They will have separate code generators for each one of them.
Does the compiler come with the code generators pre-built for all of these, or do they use a specification and a generator to generate them when required?
Okay. So, why do not we actually defer this question for some time, right, and we will come back and answer this. But important thing to know is that when you say something as a compiler, right, it includes some code generator. How that code generator is generated is a different issue. Either it could have been written by some set of people or it could have been generated by a generator, but then that module has to be a part of the compiler. That is something that we need to understand. Now, this retargetability to multiple target machines, right, you would have seen why that happens, right, why that happens, meaning like so you have these different languages. So, this is language 1, language 2 and language n, right, and then you have these different machines, machine 1, machine 2 and machine 3, right. So, the conventional approach is to kind of write from each language to the respective machine. So, that will be m cross n. You do not do that, you never do that thing, right. So, it goes into some intermediate form, right, and then from there are separate code generators for this. This is the standard approach that is followed. Now, this code generator here will simply put code generator, but it involves code generator plus a number of other phases as well, right. This code generator which is specific for machine 1, correct. Your question is it generated by a generator or is it manually written?
Yes, because otherwise I will have to have the CG for each.
You definitely have to have a CG for each. Okay. The question is whether the CG is manually generated or is generated by a code generator, right. So, code generators, if you have a code generator which can generate effective code, yes, you have a single code generator and then specify these for each one of those machines, and then the code generator would generate the CG for each one of them, right. Obviously, that is the purpose of code generator, right.
Does GCC use something like this for retargetability?
Okay, I am not very sure about the way in which things are done in GCC. I will certainly flash some slide in the next discussion